Hello, today I'm implementing logistic regression from scratch. I have a small data set here. X is ranging from -5 all the way to +5, and output is either 0 or 1. So we are supposed to build a model such a way that input, model, output. Your input is X, which is in this case is integer, and the output is Y, which belongs to either 0 or 1. So each value in this set is called a class, and since we have number of class as 2, this is called as a binary classification problem. Okay, let's get started. So as you can see, I have plotted the data set and the curve that we are trying to fit here. This is called an S-shaped curve, or it's called a sigmoid curve. Okay, so we'll start by assuming that p of x, the probability function, is linear, but p of x is unbounded. It goes from -infinity to all the way to +infinity, and to bind this, to bring this under the bounds, which is either 0 or 1, we apply the log function. And since p of x is linear, we'll take log of odds, which is p of x over 1 minus p of x, to be linear, and a linear function can be expressed as this. As such, and simplify, we'll just solve this for p of x, which should give us p of x is exponential of theta 0 plus theta 1 x times 1 minus p of x, which should give you exponential. I'll just call this term as z, and you'll have 1 minus p. So p is equal to ez minus ezp. P plus ezp is e. P times 1 plus ez is ez, which implies p of x is exponential z over 1 plus exponential z. Can multiply both numerator and denominator by this, and that will give you your probability function to be 1 over 1 plus exponential negative z. But we know that z is theta 0 plus theta 1 x. So plugging that back here, we should be getting minus theta 0 plus theta 1 x. So you have equation number 1 here, and since we are trying to predict the logistic regression, it predicts probabilities, which uh, can be fit using something called likelihood, which is given by likelihood of theta 0 over theta 1, which is the product ranging from I, it's equal to 1 through m, and you got p of xi bar yi. I have taken a Medium article as reference for this, and let's go 1 minus p of xi bar 1 minus yi here. Just do this, Let me take log on both the sides. Apply natural log on both sides. So you'll have log of loss theta 0, not loss, likelihood will be log of is running from 1 through m. M is your population size or sample size. You have p of xi to the power yi times 1 minus p of xi whole power 1 I. Yeah, and we know that log applied on pi I is running from 1 through a xi will give you summation of I is running from 1 through n log of all xi's, and that is because let me just expand on this. Your log of x1 times x2 times all the way up to xn, and we know that log a log b log of ab is equal to log a plus log b, so you'll have this, which is the same as what we have written here. So, and also we know that log of a power b is b times log a. So let's just go and expand on the right hand side. So you should get summation of I is running from 1 through m, and let me just write log of p of xi power yi times 1 minus p of xi power 1 minus yi. Yes. And then I have summation from 1 through m. So log a, log b, we can simply have log of pxi power I times log b, which is 1 minus p of xi by 1 minus yi. This will be plus, there's one more bracket here. Yeah. So summation is running from 1 through m. We'll just yi times log of p of xi plus 1 minus yi times log of 1 minus p of xi. Yes, that seems about right. Yeah, and we know that from equation 1 that we have written, p of xi is this. Let me just get a highlighter. So we have this. So substituting that back here, got 1 over 1 plus exponential. I'll just keep that as z, where z is theta 0 plus theta 1 of xi. I'll just plug it back here and here, which should give us summation I is running from 1 through m yi and log of 1 over 1 plus exponential negative z plus 1 minus yi times log of 1 minus 1 over 1 plus exponential negative z. So upon further simplification, yeah, this can be simplified further to 1 plus exponential negative z minus 1 over 1 plus negative exponential z. So we'll have these terms cancelled out, which should give us from 1 through n log yi times, and we know that log of 1 over a is negative log a, so we just got minus log of 1 plus exponential negative z and then plus 1 minus yi times log of exponential negative z over 1 plus exponential negative z. So that's good, and point to remember is z is function of z of I. For simplification, I've just kept exponential z here. And once this is done, we know that log of a over b is log a minus log b. So let's just apply that here. It should give us summation through I minus yi log of 1 plus exponential negative z plus 1 minus yi times log of exponential negative z minus log of 1 plus exponential negative z. Let's just expand this term here. Let's see what we get. Minus yi log 1 plus exponential negative z plus log of exponential negative z minus log of 1 plus minus yi times negative z plus yi log of 1 plus exponential negative z. So you see that this term and this term seems to be cancelling out each other. So this is the minus, this is the plus, resulting in a 0. And let's get back to this. So you have summation is running from 1 through n, and log of exponential negative z minus log of 1 plus exponential negative z minus yi log of exponential negative z. We know that log of exponential of a is a, because log and exponential are inverses of one another. What log does, exponential undoes, and vice versa. So we just got summation through m minus z, and we just got, do we have here minus z? Is that minus z? Did I miss something? 1 minus 1 log of minus c. Yeah, nothing. And I seem to have missed something. Let me do something before this. I'll just take, you see, there's log of easy common that I can take here. So I got 1 minus yi. Yeah, it's still the same. It's still the same. I can still take this. So it's minus z minus log of 1 plus minus z, and apply this here also. You just got minus yi times minus z. So summation through m. You just got 1 minus yi times minus z minus log of 1 plus exponential negative z, which is nothing but 1 through m negative z. Yeah, one more term. We know that log of exponential a b is a plus log b. So in this case, let a be minus z and b be 1 plus exponential negative z. So exponential a times b is nothing but exponential negative z times 1 plus exponential negative z, which is exponential negative z plus 1. So upon further simplification, we'll get this. So our final log of likelihood becomes summation running from I, and you got zi yi minus log of 1 plus exponential minus zi. Yeah, yep, that looks about right. And yeah, so there we have it. But yeah, let's simplify further. We have zi to be theta 0 plus theta 1 xi, and we'll denote log of loss by j. This is going to be our loss function, just like we had it in our linear regression. We'll try and optimize this. So j of theta 0 theta 1 is defined as summation I through m zi yi input yi theta 0 plus theta 1 xi minus log of 1 plus exponential negative theta 0 plus theta 1 xi. the right curly brace always comes out wrong. And our job is to find theta 0, theta 1 such that j of theta 0, theta 1 is minimized, or is the value is as low as possible. So we just have to, our objective is minimize. Objective is minimize j. There is no constraints as of now, and our approach will be the same, will be gradient descent. All right. This is our beautiful loss function that we have here. This is what we're trying to optimize. So same drill as linear regression. Find this, and each parameter theta I will be updated as this. Yes, yesterday I had forgotten the alpha parameter during the linear regression. So let's just get with theta 0 partial j over partial theta. What is this? Right, we'll have to take the average log likelihood. Yeah, no, just that 1 by m. All right, let's get going. Partial derivative 1 by m summation I through m. So differentiating the first term, yi will be constant when differentiating with respect to theta 0, and we know that d by dx of x is 1, so you have 1 here, and theta 1 we are assuming to be independent of theta 0, so this will be 0. Then you have minus this. We know that d by dx of log of x is 1 by x, and we are supposed to use the chain rule here. So what do we get? We have got 1 over 1 plus exponential negative theta 0 theta 1 xi times minus 1 times theta 0 is 1 again, and the other terms are simply 0. Nope, missed out an exponential. So differentiating the exponential that, and now you get minus 1 plus 0. Exponential d by dx of exponential ex is exponential itself. Alright, that looks good. So we got 1 by m summation through m yi minus, so it's exponential negative z over that. I think I missed out a 1 yesterday data. Yep. Yeah. So you just got 1 over 1 plus exponential negative theta 0 plus theta 1 xi. So you'll be multiplying both numerator and denominator by exponential positive z. The numerator gets 1. You're multiplying it with inverse of one another. We'll have this. So this is, let's call it as equation 2. partial j partial theta 0. Similarly, let's just get partial j partial theta 1, which will be 1 by m summation. You should have yi and 0 plus xi time minus 1 over 1 plus exponential negative theta 0 xi times exponential negative plus theta 1 xi times minus 1 times 0 plus xi. So this can be written as 1 over m summation xi times yi minus and minus gets plused out 1 over 1 plus exponential positive. This is what we are supposed to get. So partial j yep, and in the end we have theta u nu. What is wrong with us? Alpha times partial j partial theta 0 and theta 1 nu will be theta 1 current minus alpha times partial j partial theta 1, and I'll just call this equation 3. This term is equation 2 and this term is equation 3. So there you have it, the equations that we're supposed to implement, and the algorithm is going to look something like this. So first we'll compute best values for theta 0 and theta 1. Once that's done, we'll compute zi through theta 0 plus theta 1 xi, and we'll just find the probability sigma z and then let's say we'll be setting a threshold for the probability to be what, 0.5, and output y of I will be 1 if p of x of I, or in this case z of I, is greater than or equal to the set threshold, or it's simply 0 if p of zi is less than threshold. And as again I have assumed this to have one feature and one target. So you have the linear equation to be theta 0 plus theta 1 x, and for n number of features you'll have theta ranging from theta I and I going from 0 all the way to n. So you'll have theta 0 plus theta 1 x1 plus theta 2 x2 plus theta n xn. So for now I'll just be implementing the one feature, one target variant, and then later go for multi-class classification. Okay, so multi-class, not multi-class, that would be different, taking multiple features as input. So there you have it. Let's get started with the implementation. Yeah, all right. So we have done the derivation. Now let's just jump into the implementation part. I have the algorithm that we wrote here. Uh, let's get started with this. Let me build the code skeleton first. So class logistic regression. Let me build the init. And the fit method. And I get the gradient descent. Get the predict method. And then we need predict proba. We need the sigmoid function. Evaluate accuracy. Yes, so the evaluation metrics for regression and classification algorithms are different. Evaluation accuracy. We'll just put this as this. And representation. Looks good so far. Alright, let's get started. Let's initialize self dot theta 0 to be 0, theta 1 to be 0, status to be false, and we'll need the threshold that we set to be 0.5. Yeah, that looks good. If the if the lengths don't match, then we raise a value error saying that x and y should be of same length. And the training data cannot be 0. Training data cannot be empty. Yeah, that looks good. And as always, let's get info. Model training started. Model training complete. And here we'll be calling the model. The fit, the optimization method, which is x and y, and we'll be passing alpha 0 to be self, theta 0. It's theta 0 to be self, dot theta 0, theta 1 to be self, theta 1. And let's get with the integrations as such. I'll just copy the signature here. Yeah. Hmm, looks about right. Let's go ahead and implement these algorithms. During the export, a few expressions here has gotten split. Looks a little ugly, no issues. Let's get started. M is going to be the length of y, and yeah, no issues. For each item in the iterations, let's go ahead and do theta. One update is going to be alpha 1. Thinking of alpha minus L R by M star. Did I miss an LR? Yep, I did. Yeah, LR over M. It's theta 0. We got yi plus this. So summation of all yi's, sum of y plus 1 by 1 plus exponential that. Sum of 1 over 1 plus math dot exponential, got minus alpha minus theta 0 plus theta 1 star x for x and x. Yeah, looks about right. Yeah, yi plus this looks good. This is theta 0, theta 1 update is, let me just copy paste this. We have, yeah, so it's simply this term, everything multiplied by xi, so you get xi yi plus that. I think copy pasting this was a bad idea. Let's just make it this sum of x star xi yi, right? Yeah. So summation of xi yi for xi yi in zip of x comma y. Looks about right. So plus summation of x star, the same term, 1 by 1 plus math dot exponential of this theta 0 plus theta 1 times x. Yeah, no issues so far. Let's update theta 0 to be theta 1, theta 0. Let's go update. And theta 1 will be theta 1 update. And yeah, so for set number of iterations it will run, and let's just get with at this point the training is done, so the training status will be set to true, and we'll get into this. So we're returning none here. Let's get going with the prediction. What do we need for the prediction? We need a new input, which can be the integer or float. Let's get probabilities to be, I'll just get prediction, probabilistic predictions, and the probability of this is going to be, let me leave it there. Yeah. So same following the algorithm here. So this part is done. So compute the best theta 0, theta 1 is done. You're taking a new xi and passing that through this equation and getting the zi. So zi is this self dot alpha 1 star x. So we need a new that goes here, and we have to compute the sigmoid next, and sigmoid is given by self dot sigmoid of z. How do you calculate the sigmoid? Sigmoid of given z, let me just take z, is nothing but 1 by 1 plus exponential x by 1 plus exponential negative z. Yeah, so dot sigmoid x, and probabilities will be, for 0 it will be 1 minus sigmoid of z, and for 1 it's, yeah, this probability goes here, and class 1 probability will be probabilities dot get dot 1 comma 0. Yeah, looks about right. And if class 1 proba is greater than the threshold that we have set, we give predicted class as 1. I'll just put else predicted class as 0, and then we return the predicted class. Looks right. Let's get into the evaluation part. What does evaluation take? It takes x test and y test. If len of x test is not equal to len of y test, training status is supposed to be true. Model is not trained yet. Yeah. For I in X test, prediction is self dot predict of I, and then we append that Y prediction. Now we try to get the prediction, which is Y test. This is what this needs. Find the length, and score is nothing but you just need to check y2 ypred, not this. You need sum for the values for yt comma yp in zip of, yeah. So we are comparing each value in ytest and ypred, and if they match we get true, and if they don't match we get false. We are summing up all the values when it is true. So it's like correcting a student's answer paper, and accuracy is nothing but 1 by m score, or simply score by m, and we return accuracy. Yep, looks yep, let's get back to this. Yep, that looks about right. Let's get going with the testing part. We'll implement the example that we looked at before this. Create an instance of our class. I'll just pass x and y here, both, without any splitting. Let's say if our code produces any errors or so, and I'm passing 44 for prediction, so that should be 1. Let me look at dot predict proba of 44, and let me look at log right. Yep. Did I forget a comma? Yes, I did. Oh, did my code run in the first attempt? The accuracy, let me just round it off. Just round it out. Okay. Where does it say it's 44? Implemented the algorithm properly. Okay, I think I put a minus. Theta is okay. I think I might have missed the negative. Yes, so you see that it's producing this. Let me test it out a few more times. Let me try out something. I think C1 should have C1 just come with try. Let me try it out with a standard iris dataset and see how it goes. Simple length, simple width, petal length, petal width. No issues. Let me take X to be data of sepal length to list. Let me take I don't think this will work. All right. All right. I'll just stop it at this because Iris is a multi-class classification problem, and currently my implementation is meant for binary class classification. Yeah. So this was it. Implementation of logistic regression from scratch.